Hi folks, and thanks to be here for the session about easy improvements in your microservices architecture. I'm Nicolas Fränkel. I've been working in technical roles in development for like 18 years, and since 2 years I'm a developer advocate. I work for a company called Hazelcast, and Hazelcast has two products. The first one is an in-memory data grid, and since I will talk about it later in the talk, I will leave it at that for the moment. The second product is Hazelcast Jet, and it leverages this in-memory data grid to do stream processing in memory for very fast performance. Microservices. So I guess you are all aware of microservices right now. Even some of you might already have been implementing microservices in your companies. And just to introduce the subject, I would like to have like those lists of features about microservices. I didn't invent them, I just took them from Martin Spoller's site. So if you just want to have a deeper look, you can check the link at the bottom and read all about it. And the fun part is that the earliest points are all about technical things. And componentization, smart endpoints, this is all technical. And we are technical people, and this is how we generally address microservices. So we just check every bullet point, and so far so good, we are very happy. And the problem with this definition is when you go to the latest point, products, not projects, it starts being not a technical issue, it starts being an organizational issue. And my experience has shown me that there is no way for technical people like us to change the organization of the company to have products and not projects. And the difference between the two being that the project has a start date and an end date, and it has an allotted budget, and at the end of the project the budget must have been spent and all features must have been delivered. Whereas the product also has a start date, but it has no end date. It is like a yearly budget. And then features are added more and more. So if you are still doing projects, that's perfectly fine. But according to Martin Spoller's definition, you are not doing microservices per se. Which is fine. It's just that it's important to have the right semantics. So I will try in the talk to do the difference between a microservice and a web service. Anyway, if you are doing componentization of your architecture, meaning you are trying to carve pieces out of the monolith into dedicated services, then one of the benefits is scalability. For example, imagine an e-commerce shop, and you have done your job of putting every one of the feature, saying there is a catalog feature, there is a cart feature, there is a checkout feature, there is a payment feature. So you have made your job to put all of these features into dedicated deployment units, and you are very happy because you understand the following. Like e-commerce is a funnel, and at the beginning you've got a lot of people browsing the catalog, and you've got less people putting items in the cart, and you've got even less people doing checkout, and you've got in the end a very few people actually paying. So that means that every one of those features, they have a different usage. And if you are having those componentization, the easy benefit is you can scale those different features differently, because payments don't need to be scaled as much as catalog browsing, for example. Whereas if you are still having a monolith and you need to scale horizontally, then all of the deployment units will be scaled in the same fashion, which is not good. And this is meant, of course, as a joke. In general, if I do this joke on site, it's much better. But here, of course, I will leave you a bit of time to understand if there is a difference between the two diagrams. So as an architect, I can say bad stuff about architects. For an architect, this on the left will probably be the same as on the right. This is the same UML diagrams. And the problem with UML diagrams, or any diagram whatsoever, is it's meant to model the reality. And on the left, you can say, hey, this is an API call inside the JVM. And on the right, you can say, hey, this is an HTTP call that needs to go through all the network. And an architect will model it in the same way, but it's very different because inside the left diagram, so inside the JVM, it's not an issue. You just make a call, and then you can have two different outputs. Either it succeeds or it fails, you will have an exception. On the right side, you will get into the realm of distributed systems, and within distributed systems, it might succeed, it might fail, or it might never do anything, like you will never get a response. And the bad stuff is that when you don't get a response, you have no clue whether the request succeeded and then the server didn't send you the response, or if the request never reached the server. So those two diagrams are completely different regarding the implementation. And of course, when you start talking about distributed systems, you go through the networks. And the fun part is I talked about scalability, and some people are like doing those componentization to say, oh, now we can scale horizontally, so we will be more performant. Actually, when you are starting to move from the monolith to HTTP calls, well, you will be having a performance issue at first, because now you are not just going inside the JVM, you are doing HTTP calls, and those remote calls will be like perhaps 1 to 3 order of magnitude slower than an API call. And if you have a chain of microservices, then they will add up, and it will be really, really bad. So at first you will have a performance hit, and you will need to scale out a lot to get the same performance as before. And as I mentioned, this needs to be printed out in every office. You have those fallacies of distributed computing. And as I mentioned, the first one is the network is reliable. As I mentioned, no, you can have, like, you can make a HTTP call and never get the response, so you run into timeout, this kind of stuff. So if we want to model correctly, this is probably like that. And the good thing with this diagram is that those layers, they can represent software layers, they can represent network layers, they can represent ISO layers, this kind of stuff. And then you've got the response. Now you understand why it's super slow. And if I tell you, hey, something is slow, our first reflex will probably be to put on some caching in front of the resource we need to access. And that's pretty good reflex, actually. But in that case, one must understand that it's a trade-off. And in a lot of cases in our industry, we try to have like solutions, like one-size-fits-all solutions, and this is the ultimate truth. Be very careful. Every decision that you make has a trade-off. So if you want to set up caching, then you must accept that the data that you will get won't be up to date. And that's fine. You just need to understand it. And again, about caching, you know probably this stuff about hard things in computer science, cache invalidation, naming things, and off-by-one errors. And yet cache invalidation is hard to do. Caching, all junior developers, including myself, when we first had to set up a cache, we decided that it's a good idea to use a hash map. And actually, it starts being a good idea because it's easy to set up. Everybody knows hash maps or Python dictionaries or whatever, depending on the semantics in your language. But then when you start getting a bit more experience, you understand one thing: a hash map is unbounded. So you can put data and data and data and data, and it will grow, it will grow. It will grow so much that you might compete for memory with your software. And at some point there is, let's say, a nominal chance you will reach an out-of-memory error. That's why you should always think about this kind of stuff. So you might say, oh, I will create my own hash map with a limit, a size limit, which is a good idea also. And then you need to decide, okay, but when there is a size limit, if I put more items into the map, what happens? I need to decide on an eviction strategy. It can be the least frequently used, it can be the least recently used, it can be any strategy. You can have priority on your items in the map. And that's good. And as I mentioned, there is this cache invalidation stuff. So every time you put an item into your map, you need to decide how long it will stay there. Because if it stays there forever, then that means that basically once you've got the data into the cache, you will never read again from the real data source, which can be what you want or not. So you must decide on the TTL. And all those features, you need to code them by yourself. So my proposal is don't do it, because there are professional solutions out there. It's not only about Hazelcast, but you shouldn't do it yourself. You know that you shouldn't implement your own crypto. You probably also shouldn't implement your own caching. Which brings us to Hazelcast, and I mentioned Hazelcast is an in-memory data grid. And what is an in-memory data grid? Well, you can think it about a data structure that is distributed around the network. So I've talked about a hash map, and imagine that you have this hash map that is on a single node, and it takes a lot of memory, even if you configure it like you want it. So one of your first decision would be, hey, let's split this hash map into two, because we have two nodes, and so there is one node having half of the data and the other node having the other half of the data. And this is sharding. And the more nodes you have, the more shards you can have. Now this issue you will run into is what happens if a node goes down. That because everything is kept in memory, then you will lose the data. Which is not that bad, because actually it's caching, so you can always go to the source. But suppose you want to keep it there, you might say, hey, I want to have replication. So if I have X nodes, I want every node to be replicated at least Y time. So you decrease your chance of losing your cache. And this is not only about hash maps. You can have queues, you can have lists, you can have a lot of different data structures. So this is an in-memory data grid. And now we know about it, we can try to use this in-memory data grid in microservices architecture. The first one actually has nothing to do with microservices. It will just be database access. The second will be an HTTP call, and the third will be about session data. So first case, I assume you're Java developers, so I infer that probably you have been using Hibernate, because Hibernate is a very widespread object relational mapping framework. It's a GPA implementation, so probably you didn't use Hibernate directly, you used GPA, and just Hibernate was the implementation, and you never saw Hibernate itself. But still, you might have used it already. And the interesting bit about Hibernate is it has caches already. There are two levels of cache. The first one is implemented by default and is actually congruent to the session object, meaning that if you use the same section object to do the same load of the same entity, the first one will actually go to the database and the second will directly load from the cache, meaning you already have some caching. Now the downside of this approach is that we probably are doing a lot of web applications today, and the session object, you get it from the session factory. And in general, it's recreated at every HTTP request. It can be a filter, it can be whatever, but basically every time you do an HTTP request, you do session factory dot give me a session, and you've got the session object, meaning that if you have two different HTTP requests, well, your cache starts from null again, so there is no cache involved. So if you want to have a cache across different HTTP requests, you need to set up this level 2 cache, and this one is not enabled by default. It's an optional and it needs to be configured. And there are a lot of different integrations available. Probably you have heard about EHCache, but Hazelcast also has an integration. So this is standard cache behavior. You want to access a data, then it will look into the cache. If the key is not in the cache, it will load from the database and it will put it into the cache, and if the cache contains the key, it returns the value. And when you do a write, then it will create or update the cached value. And now let's do some demo. So here I've created a Spring Boot application, and this is a sample Spring Boot created through the Spring Boot starter. So I used a starter data GPA, I used Spring Boot starter web, I've used a specific version of Hazelcast, the latest one, and I'm using also the Hibernate Hazelcast integration. As for the database, I'm using H2. This is a pretty stupid idea to do in general, because if you put a cache in memory in front of an in-memory database, doesn't make much sense. But you can do the same with MySQL, Postgres, Oracle, whatever. And this application is actually quite simple. I have a person controller, and this person controller uses a repo. This repo is of type GPA repository, meaning I don't need to write every method. It will be implemented at runtime for me. And I have two endpoints, one that gets me all the persons and one that gets me one single person, one at a time. Here you can see that this is the normal Spring Boot application, no magic. And here is my entity, getters, setters, standard stuff. I want to preload data, so I have this data.sql that will be read by Spring Boot. So when I start the application, I will already have 3 entities in my database. Now I will start this application. And I will curl localhost 8080/1. And if I don't set HTTP before, it's going to work less good. And I will do that. Here I've got, of course, the expected console. What I did before is actually I set up the Hibernate statistic, because I want to show you that I'm caching something. So here, because the cache was completely empty, the Hibernate statistics tell me that there is one miss, of course, and there is one put. So now the cache has this entity, this first entity inside of it. And if I redo the same, you can see that formerly I had a JDBC statement, but now I have no JDBC statement. So basically the database was never accessed, and I have one cache hit. So that's pretty good. How did we achieve that? So the first is to actually annotate our entity with cache to set which region we did to put the cached entities in it. And I'm using Hazelcast, of course. So this Hazelcast.xml is integrated with Spring Boot. So when Spring Boot detects that there is such a file, it will start up a new Hazelcast instance automatically. And here we can configure the database map. You can do whatever you want. And finally, to enable the second level cache, we just say true here. Here we use the query cache, so basically we also have a second map where we put queries. So we have as the key, we have the query, and as the value, we will have a list of all loaded primary keys. And we need to set the factory region, and finally we need to tell it which Hazelcast instance will be used. And that's all that you need to do. So in a few lines of configuration, you already have caching. Regarding the query cache, you can also like preload all entities here, and now all entities are in the cache. So if I, for example, load a single entity, the 3, for example, it will hit the cache. Here it will hit the cache. So you don't need to load entities one by one. If you use the query cache and you get all entities at all, then it will put all of them into the cache one by one. So if you are using Hibernate, this is the way to go. This is very easy to set up. Now you might want to have very, very fast performance. So there is another alternative. The alternative would be to only interact with Hazelcast. So you let go of Hibernate completely. You only interact with Hazelcast. And when you do your read or you do your write, you get only through Hazelcast. And then asynchronously, you could synchronize your Hazelcast state with the database, whatever it is. Now, of course, again, there is a trade-off because it's async. Then there is no guarantee that it will be consistent, because again, if the node goes down, then you will lose your state. But then everything is in memory, and the like hard, slow stuff is done asynchronously, so you can be very, very fast. So trade-off, performance versus consistency. Second point, HTTP calls. We could do HTTP calls and cache the results manually, but it's better to use an API for that. And you might have heard about jcache. And again, jcache is a specification, and you can have multiple implementations. And one of those implementations, of course, is Hazelcast. The other is Spring Cache. And what we will be doing actually is I want to have like at first I will have the jcache, then I will have Spring Cache, then I will have Hazelcast. It doesn't make much sense. So in the demo, I will just show you that we can use Spring Cache directly and Hazelcast. But if you want to use jcache because you are not using Spring Cache, because you are in a Java EE application, for example, it works just the same. And the use case for that is, again, this e-commerce architecture. And imagine that you have all those components that are set in their own deployment units. And what happens if you want to do to get the price of some items? Then you will call the pricing service. Because prices, they are not constant throughout time. They can be discounts, there can be too much stock, so basically you want to get rid of some items, or there can be a lot of demand, so you will increase the price. So prices are in general temporary, and you need to ask for the price every time. Now imagine that for whatever reason, network partition or the Kubernetes cluster going down, or just like plain server going down, the pricing service is not accessible anymore. That means that actually your customer cannot get the price and they cannot order. And it's not acceptable in an e-commerce architecture. So what you would like to do is probably cache the price in the checkout service or even the catalog service, so that in the case you cannot access the pricing service, then you still have something to tell to the customer. The fact that the price won't be the exact right price is not an issue, because it's better to sell at a slightly outdated price than at not sell at all in e-commerce. So again, I have a small demo, and I will need to stop that. I have a Git repo. I will give it in the slides. So I will directly go to this one where I can showcase you the Spring Cache. So here I have an additional controller. I have this proxy controller, and basically I have added an in-between service between the controller and the repository. And what this caching service does is basically it uses Spring Cache, and as you can see, Spring Cache is very easy to set up. You just set at cacheable. Again, if you are using jcache, I don't remember the exact name of the annotation, but it's pretty similar. You just set the name of the map you want to use, and then when you access it the first time, it will check the key. If the key is present in the hash map, it will return you the value. If it's not present, it will execute this method and then put the key and this value into the service map. So let's try to run it now. And now I want to show you that it works. And here I cannot have statistics. I cannot show you the Hibernate statistics because it's the cache. So what I want to do is actually I will use we have a console called Management Center, and so if I start the Management Center here, it will open a web application and it will allow me to show you that actually I am caching something. So here admin so here you can see that there was this database map. Here you have this service map, so we can click on it and we can see that actually we get 1 gets and 0 hits. And now, however, there is 1 entity inside. So if we go there and we do the same requests, now we will probably have 2 gets and 1 hit, and yes, we got it. So now I'm going into the cache and I'm not accessing the database anymore, or even accessing the repo. We can do it one more time and with the second entity. So now this entity is not in the cache yet, so basically we will have 1 more get and still the same number of hits, but now we have 2 entities inside the map. So final point, when you deploy your application on a server, there is a very low chance you have a single server, because if the server goes down, what happens is, well, the service won't be accessible anymore. So what you do, you deploy your application on different nodes, and then in order for them to be accessed, you put a load balancer in front, and the load balancer has different strategies. The easiest strategy would be round robin. So what happens is, when the first time you access the load balancer, it will send you to node 1, the second one it will send you to load 2, the third time to load 1, etc., etc. Everything is good. Now imagine we want to have these cards, still e-commerce architecture, we have these cards. One way to store the data would be in a database, but in general we don't store the card data in the database because it takes a long time to access and we want to be as fast as possible. So what we are doing is actually we are using the session, the HTTP session from Java EE, and we are storing our card data there. Now this card data now lies on the first node, and if on another request we got redirected to another node, means we lose the card data, which is not good. We're back to square one. So in order to cope with that, the load balancer will actually keep the association between a session ID and a node, and every time you ask to be directed to a node, then it will check if you have the session ID and check the association, and it will always send you to the same node, so you will keep your core data. This is called sticky sessions. Now, what happens if this node goes down again? Well, next request, the load balancer will see that this node is down, and it will direct you to the other node where you have no session data. Cart lost again. So it's not good. What we want to do is actually to keep this session data in sync on the other nodes, so that if you are redirected again for whatever reason, then you will keep your data. Is there any standard for that? Unfortunately, there is none. However, Hazelcast has different integration points. So first, you can have a filter-based integration. Otherwise, Hazelcast is a Spring Session integration, so you can use Spring Session and just use Hazelcast under the cover. You don't see anything. Or you can also keep your application, your code, completely oblivious to this replication and directly configure Tomcat for that. Or here we will be using the Spring Boot embedded integration, and of course the same can be done through Jetty. So if you are using a full-fledged application server, you could go to the filter-based solution in all cases as a fallback. Let's do a demo. Here I've created a Docker Compose file, and this Docker Compose file is a load balancer and two nodes of this application. And this HAProxy load balancer, basically it's configured with round robin. So it's exactly as I described earlier. On the first request you will go on node 1, on the second request you will go on node 2, and then on the third request you will go to node 1 again. And in order to show you that this replication works, I've created another use case, which basically is a controller, and this controller, every time it's accessed, it will use an object to get a session data that is set into the session. And this session data consists of one ID, which basically boils down to the gsession ID, and a counter. And every time I access this endpoint, I increment this counter from the session. So that means that if I have no session replication on the first request, I will get on the first node and it will return me 1, and on second request I will get to the other node, and because there is no session data, it will return me 1 again. Then back to node 1 it will return me 2, and back to node 2 it will return me 2 again. If I have session replication enabled, then I will be like 1, 2, 3, 4. So let's check if it works. I will Docker Compose up. This will create this architecture of one load balancer with HAProxy, with round robin and two nodes. Takes a bit of time to set up because the load balancer needs to understand that everything is up. And also I have the management center just in case. And at some point it should work. Yes, normally everything right now is okay. So Tomcat 1 is up, and normally Tomcat 2 is up too. Now let's try it. And I have this session stuff. So I will increase the font just because it's easier this way. So I have this count of 1, node 1, and now if I refresh I should have 2. Yes, 2. And then 3, 4. So every time I go to a different node, but I still keep my session data. And this is quite easy to set up actually. The configuration is as sparse as that. So here I'm using the customizer from Spring Boot, but as I mentioned, you have different integration points. So I have this web server factory customizer that uses the Tomcat servlet one. You can have a Jetty servlet one if you are using Jetty. And here I create a session manager. I configure it and I set it into the context. Here I'm using setSticky to false, which basically forces synchronization every time there is an access. So I'm sure I have the latest data. But of course, in general, you have sticky sessions enabled, and by default, here it's true, so you don't need to do as many checks and put as many logs in place. This was for demo purposes. So time for some takeaways. So first, microservices architecture are good, but then you are put at a cross between scalability and performance. So you will scale easier, but your performance will actually downgrade a lot at the beginning. In order to cope with these performance downgrades, you need to set up caching, and it will be at the cost of stale data. And of course, Hazelcast INDG provides you several ways to get your performance to improve your performance. So it will be database access that is easy to set up, HTTP calls, or session replication to improve resiliency and consistency. Thanks for your attention. You can read my blog, you can follow me on Twitter. If you want to know more about Hazelcast, we have a site for that. And if you want to take this repository and play with it by yourself, so it's on GitHub, and you are welcome to do that.